today we are going to do section 4.9, Newton's method. What it is a neat trick that helps us find roots. That is, when the equation goes to 0, we need to find out which x's will make the function go to 0. Those are called the roots, right? And we need to hunt them down. Now, normally what we do is we factor or something, come up with some trick, and then set something equal to 0, and then it comes out. However, a lot of times, if the function isn't cooperative, then none of the tricks work. and then what? So then here's this neat trick that Newton came up with. Now please look at page 473, and where we will look at the trick. What happens is that we are going to approximate it, okay? And we are going to approximate it with the principle of the tangent line. So let's look at this graph on page 473, and I will draw one right here, where you have some kind of a function, and it has a root, okay, some function like that, and the root is right here, but you can't tell exactly where it is. So what you do is you find a point that's close to it. I will pick a point over there, even though it doesn't look that close, so that you can see what the tangent line does better. So we'll pick a point that's fairly close to the root. Then we will find the tangent line at this point. And that you do by the standard tangent line equation, which is y equals to f of x 0. This point that we pick is the first point. We'll call it x 0, okay, for a reason, because x1 is coming. Now, so anyway, the initial point we pick, we'll call it x 0, and then we'll draw the tangent line down, which is a straight line that hits here, okay, and then which the tangent line, as we have done so many times already, is given by f x 0 plus f prime of x 0 times x minus x 0. This is the point slope formula. That is, the tangent line is a line that goes through this point with the derivative of the point as the slope, f prime x 0, okay? That's the x 0. So in all this stuff, x 0 are the fixed points, and x is the variable of this particular line. It's just a straight line. And then we figure out, well, this particular tangent line will hit the x-axis at some point, and we'll call that point x1. And what is x1? X1 is the result of setting this equation equal to 0, and if you do that, we will come up with something like this, okay? And I will skip the details of the basic algebra and just say that if you set the equation equal to 0, then x1 will be equal to x0, and then minus f of x0 divided by f prime of x0. That is, if you set equation to 0 and then solve for x, then eventually this will come out. Now at that point, we are in possession of x1. And what are we supposed to see? You notice x1 is quite a bit closer because, well, as you notice, as the graph gets past the 0 and then go up, it's slanted. So the tangent line will often make you closer to it. And then you continue doing this process. And then x2, you crank out another x2, you plug you do the same thing, okay? That is x2, it will equal to x, you bump everything up. So what happens is you find the new point and do the same process again. And so then x2 will be equal to, replace every x0 with x1, equal to x1 minus whatever this stuff is, x1. That is, you draw another tangent line down that's even closer, see? And then you have the next point that's even closer. And then you continue to do this process until you get ideally, you will get unusually very close. In fact, you get very close very quickly, as you can see. I only did it 2 times, and this is already looking pretty good. And because we came from clear over here, right? And 2 times later, x2 is already so much closer. So so you continue to do this process, and the process has a name to it. It's called to write the whole process is called xn equals to xn minus 1 minus f of xn minus 1, okay, and f prime of xn minus 1. So the n minus 1 represents the previous points, and then the n represents the current point that you're shooting for. All right, so as you can see, this is a fairly simple process as long as you can, once you calculate the derivative, and then out comes your root. So it's quite neat. So let's look at, let's look at example 4.46, which I will also assign as homework. I will talk about it, but will not actually do it myself, because it's good for you to, well, there's no point for me to punch in all this stuff right now when you can punch it in at the comfort of doing homework. So, but we will talk about it. The example 4.46 is exactly what we're talking about. Is you have some polynomial, okay, x cubed minus 3x plus 1. I'm at page 474. I should write that down. This is example 4.46, which is for your homework as well, but I'll talk about it briefly. X cubed minus 3x plus 1, and then what are you going to do? You're going to figure out what f prime is, the formula of it, and then you are going to go through this process, and you're going to find some root. Now, for this problem, the book actually tells you what they want x0 to be. You just choose one. And then you plug it into your formula, and out comes a whole bunch of stuff. Okay, so if you go through this process, then you get a bunch of answers. See, let's see, yeah, all right. So you get that doesn't look okay. So you get a bunch of answers that approach. As you can see, the answers approach a certain value. And in fact, it approaches very quickly too. See, by the third iteration, you're already at the third decimal point accuracy, right? So so it works very neatly, nice and neat. And to create that chart, I highly recommend that you use the spreadsheet. Well, I haven't done it yet, but I assume the spreadsheet shouldn't have any problems doing this. That way, you type in the formula and just drag it down, and the whole thing will pop out. All right, so that's example 4.46, which please do that as homework. And the same with the rest of the homework examples, the 4.47, 48, 49. Please do them all as homework. And they are fairly standard. See, 4.47 is about the same thing. You find the derivative, okay, and then you follow this formula and use the spreadsheet and crank it all out. Now, if you don't want to use a spreadsheet, and you have the TI-84, you know, this thing right here, and you insist on using it, that's okay too, because the TI-84 does have a programming function. They call it programming, and there's nothing programming about it. You just typed in the formula, and then you type in the input, and out comes the output. And so then you have to do that every time, instead of unlike the spreadsheet where you just type it in once and then pull it the whole thing out. Okay. So and in my this video description, I mentioned Google Sheets, so you can use that one or some other one. Doesn't matter which spreadsheet you use. And the Google Sheets is free at this point, so and I find it to be a very nice little tool for basic things. All right. So next example, we look at sometimes when the Newton's method doesn't work. Well, when doesn't it work? Well, it doesn't work if your initial guess is way out in the nowhere. Okay, like this example. All right. Like for example, oh, actually no, that's not necessarily true, I guess. For example, that sometimes there might be a mishap in the Newton's method. For example, like this case, like you have x0, okay, and then you're looking for the root that's called root sought, and you ended up it just happens that the tangent went somewhere else. That is possible. How do you handle that? Simple. You just you need to get a little closer. Your x0 is too far away, is what that means. And if you pick a better x0, then things will look much better for you. That's the idea. Nowadays, of course, we have the graphics calculator, and we don't need to, do this. The graphics calculator will type in any function, and out comes the root and everything. But we learned about the Newton's method to know how the graphics calculator can do that kind of thing. In fact, I think the TI-84 might even have a root-seeking function or something, and it probably just used this exact trick. Yeah, but anyway, knowing the pitfalls, something like this, then you have to know what you're doing. That is, you might have it look for a root, but you better know where the root approximately is. So if the root is found, you found some other root, then your x0 wasn't close enough. So yeah, or sometimes, of course, look at the next example. Okay, example 4.48, where you're seeking, where's the root? I don't even know what this is. Approximation. Okay, that you're looking. See, look at this function here. Okay, it has a root way over there at around -2, right? And where are you looking for the root? You're looking for the root at +1. So you're not getting there like anytime soon. Well, that's because your starting point is way too far away. Basically, if your starting point is close enough, you should be fine. Most problems happen because you didn't have an idea where the root is, so you're just shooting blind basically. So as long as you know roughly where the root is, then you shouldn't have any problems. And so the Newton's method is a very neat trick, right? And also effective, because it doesn't take many iterations for you to pull out the root. Although with the spreadsheet, you can pull out as many iterations as you want. 10 of them just in 1 second, just by pulling your mouse down. Anyway, so that's that. And if you don't know how to use a spreadsheet, make sure you find some YouTube videos, something to learn how to use it in a basic way, like what I'm talking about, just to have it repeat some function. Now, example 4.49, finding. Okay, this particular thing, there's actually a name for it. It is called the iterative process. Okay, iterative, that means, well, repeat. Now, for example, let's look at example 4.49. You have a function, a very simple function, and they want you to keep cranking, do this thing here. Okay, that is, in general, they want you to stick in. That is, you have a function called f of x, right? And you put something in here. You stick x0 in here, right? And out comes something. Let's call it x1. And then they want you to stick x1 in here again. The same function. That is, x1. Then you put it into the same function. And then out comes x2. So you keep cranking. That is, you keep putting the result into the function itself, so that you come up with more and more stuff. And that's what we call iterative process. And sometimes it might come up with something. It might approach something. Okay. For example, that is what example 4.49 is. So please do example 4.49 as your homework on the spreadsheet. I recommend a spreadsheet where you see you do like what is that? How many? Well, about 8, maybe 8 or 10. You crank the formula 8 or 10 times. Okay, basically you keep plugging in the new value into the function and crank out even a newer value. And as you notice, this particular function, the value approaches a certain point. That is, yeah, and that matters. It doesn't matter what that matters. Okay, the point is, in this particular case, it does approach a point, and that's the end of this section. Now, for homework, then please do problem 423. That's it. That's the end of this section.